The name of this video is Method of Images Dipole. This is the second video of a series of videos on the method of images. In the previous video, we revised the concept of electrostatic induction. In particular, we attempted to redefine the operative definition of electrostatic field, and we found a loophole in that definition, which is the usage of the test charge. You need to be very careful when setting up your test charge. So, at the end of that video, we set up a Poisson-Dirichlet problem, which is a very complicated, mathematically speaking, problem. To solve what problem do we want to solve? We wanted to solve the problem of a semi-infinite slab of conducting materials. So space on the right-hand side is filled with the conducting material in ME, and on the left-hand side there is vacuum with just one single point-like charge particle in space, which is facing the face of the semi-infinite conducting slab. And we want to find out what is the electrostatic field in this configuration. And so instead of using the external Poisson-Dirichlet problem, which is very complicated, what else can we use? Well, let's take a little tangent, a parenthesis before getting there. In the beginning of this course, as well as in 242, I asked you to revise the concept of electrostatic dipole by means of Coulomb's law and the superposition principle. Then eventually, later on, we also studied the dipole using the multiple series expansion. But right now, I want it really simple. I just want that you revise one more time the electrostatic dipole balance with a positive plus q and a negative minus q charge at a distance d from each other. What is the electrostatic field, to be more precise, in space? You should have answered this in one of these Piazza questions at the beginning of this course, in the introduction of this course. But let me here review it with you. Okay, so let's consider that we have a positive charge somewhere here in space. This is my positive charge plus q, and at a distance d from it, there is a negative charge minus q. The distance we call it capital D, not to confuse it with dx, dx, dy, and dz, etc., or dr, okay? So let us assume that these two charges belong to the y-axis of a Cartesian three-dimensional coordinate system x, y, z, and I will only sketch here the y and z axis. So this is the y-axis. The z-axis, eventually, the x-axis points towards me, and so the z-axis, let's say, is just normal here. The origin, we set it to be right here, which is in the midpoint in between these two charges. So this is my z-axis. I will not sketch the x-axis for simplicity. Continue down here with the z-axis. Therefore, the distance here between these two charges, d half, I'm going to write down the points in this coordinate system, so I'm not going to sketch it here, not to overcrowd this sketch. This is the origin. That's the only thing I'm going to write down here. And this is the positive charge, this is negative charge, point-like charges, and this is the configuration we want to study. So in particular, let's assume that the positive charge plus q is associated with a source point, capital Q1, which by definition in this case is going to be 0 on the x-axis, capital D half minus capital D half on the y-axis, and 0 on the z-axis. Similarly, so this is the positive charge plus q. What about the negative charge minus q here? Well, the negative charge minus q, let's hypothesize that is at a point here, capital Q2, which by definition is going to be 0. This time is plus d half, 0. It's on the right-hand side here with respect to the origin on this y-axis. Okay, so this is the configuration we are looking at. All right. So a generic point capital P in space, if I want to examine here a point capital P in space, which is what I asked you in one of the first videos in the review in the introduction to PhYS 342, well, point P, by definition, is an observation point. So if you look at the Coulomb's law approach to this problem, this we call it XP, YP, ZP. For simplicity, let us just call it X, Y, and Z, just for simplicity. So the running variables X, Y, and Z are the variables of my observation point capital P. I drop the subscripts capital P's for simplicity. We already defined the source points of these two single point-like charges in space. So now we are in a good shape to find the electrostatic field E1 due to Q1. This is given by 1 over 4 pi epsilon naught. X divided by a factor alpha, which I'm about to define, along the x-axis, plus, now the y-axis is the only one where we have a source charge, so it's minus d half, so it's y minus minus, so it's y plus capital D half divided by alpha, uy, and on the z-axis, so this one is uy. And on the z-axis, finally, we have plus z divided by alpha u z. What about this factor alpha? Alpha is nothing but, in this coordinate system defined here on the left, is nothing but x squared plus y minus minus, so y plus d capital D half square plus z square, the whole quantity, to the usual factor of power of 3 half. All right. What about the electrostatic field E2 due to the second point-like particle with charge minus q in that case? So in that case, we have minus 1 over 4 pi epsilon naught. And the rest of the structure here is very similar. It's going to be x divided by beta ux plus, now is y minus d capital D half divided by beta uy. And finally, we have plus z divided by beta uz. And as always, beta, in this case, I will let you actually calculate beta. So please calculate beta in Piazza. So what is beta? Please do this in Piazza, okay? All right. So now if we do the linear superposition, so we linearly superpose these two fields, we obtain the total field, which I can sketch here, the field lines, I can sketch them here. They go obviously from the positive to the negative charge in this fashion. This is one simple line. You can sketch this with Wolfram alpha, for example, as I've asked you to do already in the beginning of this course. And then, for example, we have this field line here, and we have this field line. And let's do one more. Okay, so they go all in this fashion. Okay, here they enter this way. And similar here, there will be a line which goes this way and comes back in here in this way. And of course, you can do the same thing on the other side. It's all symmetric. Again, I urge you to do this in Wolfram alpha, for example. It's very simple to plot these field lines. Okay, and so on. This way. Great. So now we have the field lines. Of course, this is all a symmetric problem. So again, I urge you to plot it to convince yourself that these are the field lines. for the electrostatic field associated with these two positive and negative charges, this dipole, okay? And so what about the equipotential surfaces? Well, the equipotential surfaces are very simple to be sketched here because they need to be normal at each point of the field line. So for example, this one happens to be an equipotential surface. This z-axis here, this we call it capital sigma A. This is an equipotential surface, okay, for this problem. Similarly, a more complicated one could be, for example, the surface which passes through this point P here, so something like this. Etc. So this is also an equipotential surface, okay, and is normal at each point. If you compute there the electric field, for example here, it's easy to see that. So this electric field line and this equipotential surface form a 90-degree angle, okay? So this is another equipotential surface which we call capital sigma B. It's more complicated, of course, compared to capital sigma A, but it is also simple to sketch it. You can also mathematically, if you want, derive the equation associated with it because it has to be normal to the field lines which are given by the superposition of these two equations here. You can also plot it with Wolfram alpha quite simply. All right, so now with all that in mind, this seems a rather innocent problem. What is the connection between this problem, which is an electrostatic dipole balance plus Q minus Q, nothing else, vacuum in space, with these field lines and with these equipotential surfaces? What is the connection between this very innocent, straightforward FIS 242 problem with these electric field lines and the complicated problem of a single point-like charge plus Q in front of a semi-infinite slab of conducting material? Well, let's do the following Gedanken experiment. So a Gedanken experiment is an experiment where it's a thought experiment, okay? So it's from German, and this idea was developed in the 20s and 30s, and probably even before, in the German physics community, and is still used very much nowadays. And so the Gedanken experiment I want to do now is as follows. So it's a theoretical experiment, if you want. And so we take a very thin sheet. Let me write down the instructions here. So we take a very thin sheet of conducting material in microscopic electrostatic equilibrium and we shape it. So we shape, okay? For example, you can take aluminum foil, like the one you use to wrap food, okay? It's very easy to shape it. So I shape aluminum foil, which is a thin conductor. Of course, mathematically, in this Gedanken experiment, we want zero thickness, okay? But a very thin conductor we do as well. And so we shape a thin conductor in macroscopic electrostatic equilibrium to have exactly the same shape as the mathematical expression, the curve sigma, capital sigma B, okay? So I take aluminum foil. I know what this, my math gives me this this equipotential surface, and I shape it exactly in this form, okay? So in 3D, you need to imagine to really shape it like this, okay? You need to shape it in 3D, which is a little more complicated, but this is the cross-section on this board, all right? So that's the first step of this recipe, okay? We shape a thin conductor in ME as the shape of capital sigma B. Of course, I could also shape it at capital sigma A or any other equipotential surface. The next thing we do, we set the electrostatic potential V on this sheet of conducting material to be exactly the constant V on capital sigma B, which we know it's nothing but a constant VB. Okay, it's a constant because it's an equipotential surface. So we know from 242 that changing the charge on a conductor, we can tune its potential and vice versa because they are related by the capacitance, which is the constant ratio between charge and potential. So we can tune up the charge and therefore the potential on this conducting sheet, which I'm going to place eventually here in space, to be exactly the same value as the electrostatic potential constant on the sigma B, which I can compute mathematically. Good. So now we have a thin sheet of aluminum foil where we tune up with a battery the potential to be exactly that of this equipotential surface, which is an equipotential, so constant potential VB. The next step is that we place the sheet in the location of capital sigma B. Okay? So we take it, we place it there. Now, suppose that I'm observer, so what is the situation here? We have a plus charge plus Q, and minus charge minus Q. This remains the same. They generate a certain field which I can measure experimentally. I place the thin conductor at the potential VP constant in equilibrium in this region of space, which coincides with the location, with the physical location, with the geometrical location of capital sigma B. If I'm an observer now, does it change anything at all, this addition of this sheet? Of course not, because it's just an equipotential, and it basically does absolutely nothing to this problem. So the field lines will remain the same, except for a simple caveat, which I'm about to say. The only way to tell that there is such a conducting sheet is to poke it, to touch it. So I need to observe it somehow, I need to touch it. Otherwise, it wouldn't be there. I mean, it's like if it wasn't there, okay? So the only way to probe that there is this sheet, I need to touch it, okay? So to measure it somehow. And so this, I would say, it's quite a beautiful result, because apparently what we ended up doing by means of this simple recipe here, we ended up solving the problem of a single positive point-like charge plus Q facing an infinite sheet of conducting material in front of it. And so there is electrostatic induction, and so there will be a charge distribution, fairly complicated in this case, negative, of course, associated with this sheet here, and it's going to be concentrated more in this region, and then it's going to be less concentrated and less concentrated as before, as we've seen already for the semi-infinite slab. There's going to be a negative charge on this, and that's the problem we have solved. So eventually, we solved exactly the problem of a super complicated problem of a single positive point-like charge in front of a conducting sheet. Now, remember that this conducting sheet is basically such that the bending radius is approximately plus infinite. So it's like a big sphere, if you want. Okay, so it's a structure with an infinite bending radius, or at least very large. Okay, mathematically here would be infinite. And so, so what kind of problem have we actually solved in this case? Well, this behaves as an electrostatic shield, right? It's a conductor in equilibrium. So it's like a shell, okay, with an infinite bending radius, but eventually closes the entire space here on the right-hand side, which encloses the charge minus Q. An electrostatic shield, what does it do? Splits the space into two regions which don't interact with each other. So the region on the right-hand side here, where the minus Q is located, doesn't know what's going on the left, and vice versa. So what happens if we decide to fill up this entire region of space with a conducting material? Well, this will still work, because it's the definition of electrostatic shield. So I can choose to fill up either the region here on the right-hand side and leave the left in vacuum with this positive charge plus Q, or vice versa. I could fill the left region and keep this in vacuum. Okay? Electrostatic shield splits these two regions into independent region of space, okay? Because of this infinite or very large infinite bending radius, mathematically, in this case, okay? It would work also if it were just very large, in a real experiment, let's say. And so what we ended up solving here, these field lines, these red field lines here, which start from plus Q and end up on this surface, and now I cancel them out because inside the conductor in equilibrium, there are no field lines, there is no field, there is only a charge, negative charge minus Q distributed on this surface, capital sigma B, which opposes electrostatic induction plus Q. These field lines, of course, are normal at each point on this surface, because clearly this is the situation, because this is an equipotential surface, and it's also the surface of a conductor, which has to be an equipotential surface. So we have these field lines which end up to be normal on the conductor as expected. These are the field lines of a very complicated problem, the one of a positive charge plus Q, in front, next to a big hard sphere of a conducting material in macroscopic electrostatic equilibrium. So imagine that. We ended up solving such a complicated problem by means of just the dipole problem. And so this charge, which we need to place in here to find these field lines, and again, I cross them out in the conductor. So what is left is really the field distribution for a plus Q in front of a conductor. So this, we call it the image charge, okay? So this one is called the image charge. So if you want this method of images in nothing but a sort of retro-engineering approach, So originally, what people attempted to do, okay, let me go the other way around. So let's say we are 100 years ago and we don't have COMSOL to solve this problem. We have a point like charge plus Q in front of this huge hard sphere, okay, of conducting material in ME. I want to find the electrostatic field lines, the field lines for this complicated thing. Either I solve the Poisson problem similar to what we said before, or people started to think, so what is, by retroengineering, a charge distribution which mimics exactly this field lines configuration? As it turns out, that of a dipole, I place a minus charge right there, and I end up finding the field lines which are exactly the same. So it's a retroengineering problem, a beautiful problem. Okay, another specific case is that of, instead of considering the sigma b, what we are going to consider more in detail in the next videos, we can consider capital sigma A as the aluminum sheet I'm going to place there, fill up with conductor everything on the right hand side, and so we end up solving the problem of a plus Q in front of our semi-infinite slab, okay? And so these field lines will be exactly the field lines of that problem. And this is what we are about to use in the next videos to find, for example, the charge distribution on minus Q, how minus Q is distributed on capital sigma A in the case of semi-infinite slab. Okay, so to summarize this video, this is the method of images dipole. It's a retroengineering problem. So to summarize it, I go backwards. I want to solve the problem of a conducting hard sphere in ME in front of a charge plus Q, or if you want a semi-infinite slab of conducting material, in that case I need to cross everywhere, including here, in front of this plus Q. How do we do that? Well, as it turns out, if you think about it, it's nothing but a plus Q minus Q dipole problem with these field lines, where I substitute an equipotential with a thin conducting sheet, and then it's an electrostatic shield, and I can split space into two independent regions, which allow me to solve the problem readily. And this is in fact the mathematical solution. So if I block it right at the conductor, that's exactly the solution of this complicated problem. And this is the recipe you need to follow. I know that there are always some issues with this, but it's really just, you need to think about retroengineering, okay? So people didn't have complicated advanced software to simulate such a thing, and they found out that the field of a dipole actually solves it, as clearly this recipe shows. So I really find this absolutely amazing. And in the next series of videos, we are going to find exactly mathematically the charge distribution sigma, how it is distributed here. And already we clearly can imagine that it's going to be more densely distributed in proximity of Q, plus Q. Electrostatic induction goes with distance, and more sparse when we go away. And so that's the function we intend to find, which when integrated should give the minus Q. As an exercise, you could also do it, find the charge distribution for a more complicated shape, but we're going to do it only for a semi-infinite slab. That's it.